Mine's already blown.
When you do the calculation of how much of this lightest supersymmetric particle should be left over since the Big Bang, it exactly matches what you need to be the dark matter. When you look at a theory called supersymmetry that I've spent a long time working on, within this theory, which goes beyond what we know about particle physics for reasons that are well motivated.
Because that's ordinary symmetry.
That's right. It takes the symmetries that we have and it takes them one step further, and it's the only step further that you could possibly go. So, of course, nature must make use of this final symmetry principle. Why else would it exist? That's the thinking that we've had.
Wait, just let me back up for a minute.
Yeah.
As I was learning particle physics, I was intrigued to recognize that you have your electron, you have your photon, you have your neutrino, and these other sort of basic particles. And they exist in our world that we experience. If you up the energy knob, other particles manifest. There's a version of the electron that manifests only in these higher energy levels, and it's called a muon.
Right.
Okay? So there's a whole layer of particles sitting above the ones that are in our world.
Right.
So there's 3 of these layers. And tell me the 3 electrons.
You get the electron, the muon, and the tau.
The tau.
Yeah.
Okay. And there's an electron neutrino, there's a muon neutrino, and there's a tau neutrino.
Yeah.
Right.
So now I have 3 layers here, and you have access to them in your particle accelerators because it takes a lot of energy, and you can get there.
Yeah.
Okay.
Right.
And tell me the three force carriers. We have a photon.
You got the photon, then you got the gluon, and the W and Z bosons, or the weak nuclear force.
Okay.
And then for the quarks, you got the up and the down that we spoke about. You got the charm, the strange, you got the top and the bottom.
Right.
So again, they come in 3 pairs of 2.
quarks.
Yeah.
Okay.
Yeah. Supersymmetry says take all of those particles and double them. Another shadow version of all of those particles.
So I didn't know this. The entire set of particles would have a counterpart in this supersymmetric place.
So for the electron, you have the supersymmetric electron. For the quarks, you have squarks. For neutrinos, you have sneutrinos. But here's the thing. This is all mathematically motivated by a completely compelling rationale. So this is not pulled out of, thin air.
Thin air.
We have our universe 3 ways, a 3-layer cake. And there's a whole other cake. Where does that live?
With us, but we believe they're more massive, which is why we wanted to build the superconducting super collider to try to find them. Now, we've looked for these at the Large Hadron.
If they're more massive, why aren't they right here in front of our faces?
They typically have short lifetimes, so they'll decay into lighter particles. But the lightest of the supersymmetric particles would not decay, and therefore it should be all around us.
Tell them why the lightest one would not decay.
If it's the lightest one, when it decays, the decay products have to be lighter than it. Well, the lightest supersymmetric particle would be stable, should be around us.
That's what everybody's
so maybe
looking
it's
for?
filling space.
Right.
And here's the beautiful thing. This will blow your mind. When you do the calculation of how much of this lightest supersymmetric particle should be left over since the Big Bang, it exactly matches what you need to be the dark matter. It comes in the right abundance.
Dang.
And yet we've not found it. And it may be the wrong answer. So sometimes things that just seem so deeply compelling are wrong, but we don't know yet.